Swayam Prabha. Digital India. Educated India.
Friends, let us consider the example of a complex reaction by looking at one specific network which is both important practically as well as gives an elegant way of analyzing the chemical reactions. So, what we are going to do today is look at monomolecular reversible reaction network. So, what is monomolecular reversible reaction network? Let us say that we have n chemical reacting species. So, these are our chemical reacting species, n species, and there are reactions between these n species which can be represented by AI going to AJ. I and j are anything between 1 to n. Of course, they cannot be equal because A1 going to A1 does not make any sense. So, we are looking for example reaction networks which are A1 going to A2, A2 going to A3 and so on. These are called monomolecular reaction networks because both reactant side and product side the molecularity is 1. They are reversible reactions. So, we have monomolecular reversible reaction network. Now, one may ask what is the importance of these kind of networks. Number 1, there are certain reactions which actually follow this monomolecular reaction network. For example, 1-butene, cis-butene and its isomers and trans-butenes. So, we have 3 species, n is 3 and there are reactions of this kind between these 3 species. So, and monomolecular reaction network which is actually a real reaction, but also it is important because many times we can take this monomolecular reaction network as a typical example of a simplified complex network. So, let us say that we have a reaction, real reactions are something like this: A1 plus A2 going to A3, A3 plus A2 going to A4 and so on. We will see in the next example that we can actually write this reaction network, represent this in an hypothetical reaction or a simplified reaction network like B1 going to B2, B2 going to B3 and so on. B1, B2, B3 are not real species, they are hypothetical species, but they contain all the information that is there for the real network, that is in the species A. So, from that point of view analyzing these networks is important. So, let us take an simplest type of this reversible monomolecular reaction network and see what kind of results we get for this network, and then we will generalize those results. So, let us start with what is the simplest network possible. There has to be minimum 2 species, nothing can be simpler than that. So, for a reaction A1 going to A2, A1 going to A2, this is the simplest kind of monomolecular reversible reaction network that one can think of. So, we will write this reaction network and the kinetic rate constants for this forward and backward reaction using the following notation. Since we are getting 2 from 1 in the forward reaction, let us call this reaction rate constant as K21, and the backward reaction we are getting 1 from 2. So, let us call this backward reaction rate as K12. Let me also simultaneously generalize this, so that we need not come back to the notation once again. If we have a reaction AI going to AJ, let me write it down. If I have a reaction AI going to AJ, formation of J from species I, the reaction rate constant is Kji. Formation of species I from species J, reaction rate constant is Kij. So, that is our reaction network in general. So, if I have this reaction network, so let's go back to this is a general case, we will come back to that little later on. So, if I have a reaction network, and let me rewrite this so that we have enough space to write things. Let us say my reaction network is A1 going to A2. I am calling the forward reaction as K21, the reverse reaction rate as K12. So, now let us try to work around the kinetics of this process, but this time instead of using concentration we will use mole fractions. It is one and the same thing, because concentrations, by taking the individual concentration and dividing it by the total concentration, we will get the mole fraction. So, we will write this kinetics in terms of mole fraction. So, let us write dy1 dt, again a closed system, dy1 dt, that is y1 is the mole fraction of species A1, will be minus K21 y1, the forward reaction, plus its generation K12 y2. Similarly, we can write dy2 dt as K21 y1, its generation from species 1, minus K12 y2. So, we have these two reactions, two mass balances 1 and 2, and let us play around with this mass balance little bit. So, we will say that we will add 1 and 2. If we add 1 and 2, what do we get? We get d dt of y1 plus y2 equal to 0, because we know the mole fractions cannot change, and indeed if we add these two equations we will get 0. But this 0 I am going to write it as y1 plus y2. Why? Reason will become clear in a minute. Let us also do another manipulation. Let us multiply the first equation by K21 and subtract it by multiplying second equation by K12. So, we are multiplying this term by K21 and then subtracting minus K12 from this term. Now, if you do that and little bit of rearrangement, we will get d dt of K21 y1 minus K12 y2, that is the left hand side, and the right hand side if we manipulate little bit we will get K21 plus K12 into K21 y1 minus K12 y2. Okay. So, we have chemical species A1 and A2, its dynamics being represented by mass balances 1 and 2, and we have manipulated this mass balances 1 and 2. Now, let me now relook at these equations, these two equations, and let us say that I define zeta naught as y1 plus y2 and zeta 1 as k21 y1 minus k12 y2. Okay. So, if I do this and I also now call, if I do this, okay, if we go back to our equations of these two equations and defining zeta naught and zeta 1 in this manner, we see that the dynamics is represented by zeta 1. So, we have two equations zeta naught and zeta 1 dynamics, which is represented in this manner. Now, what is the motivation for doing this? The motivation for doing this is that I am now going to say that I have two hypothetical species B naught and B 1 whose compositions are zeta naught and zeta 1. These are hypothetical species, these are not real species. My real species are over here and the real reaction. These are my hypothetical species. Now, why do we need to do this? We need to do this for the following reason. If you look at the mass balances of the real system, they are coupled y1, y2, y1, y2 and so on. So, the original species dynamics is coupled and it is not very easy to see what is happening there. But the same dynamics for hypothetical species is completely decoupled. Zeta naught equation has only zeta naught, zeta 1 dot equation has only zeta 1, and if there are many more species, you will always find that that will be the case. Or in other words, what we have done is we have uncoupled the original dynamics, uncoupled it, but not for the real system, but for the hypothetical system. So, now what is the reaction involving these hypothetical species? If you look at this, we can write these reactions as simply B naught going to something, B 1 going to something. What is that something? I do not care, because if I had told that my system reactions are B naught going to something, B 1 going to something, its concentrations are zeta 0 and zeta 1, then you would have written its kinetics zeta naught as some kinetic rate constant times zeta 0, zeta 1 dot another kinetic rate constant times zeta 1. And the solution of this is fairly straightforward. How do we solve this? So, what I am going to do, let me see. Okay, let me go back. Okay. So, what I am going to now do is I am going to now look at this hypothetical system. Okay. Although I have my original system, but what is this hypothetical system? What is the solution of this hypothetical system? This one particular over here. That is very easy. So, my reaction for hypothetical is B naught going to something, B 1 going to something. Its solution is zeta naught is constant, and if you look at the definition of zeta naught, that constant mole fractions must add up to 1, and zeta 1 is zeta 1 0 e raised to minus k 2 1 plus k 1 2 into t, because this is simply zeta 1 dot equal to some rate constant minus some rate constant times zeta 1. Now, if we know zeta naught and zeta 1, we can always regenerate our original system by inverting these relationships. That is, if I know zeta naught as a function of time, zeta 1 as a function of time, I can always find y 1 as a function of time, y 2 as a function of time. So, even though my original system is coupled, by decoupling the system in terms of hypothetical species, I am able to get the complete solution of y 1 and y 2. These are simply linear relationship, y 1 plus y 2 is zeta naught, we know what is zeta naught 1, this k 2 1 y 1 minus k 1 2 y 2 is zeta 1, we know what is it as a function of time. So, let us see what we did now in a more general sense. So, let us go back to our original system, and we could have written the dynamics in a compact form y 1 y 2 as minus k 2 1 k 1 2 k 2 1 minus k 1 2 into y 1 y 2. The same mass balances written in a more compact form. This can be alternately written y dot equal to stoichiometric coefficient reaction rate coefficient matrix K times y, this particular mass balance equations. Now, what is the link? Why are we doing this? We are doing this to find out how do we get this rate constants of this, what are this 0 minus k 1 2 k 1 plus k 2 1, what are they? It turns out that the eigenvalue of this matrix K, eigenvalue of this matrix K is nothing but 0 and k 1 2 plus k 2 1, this number over here are the eigenvalues of matrix K. So, eigenvalues is one is 0, the other one is k 2 1 plus k 1 2. Okay. So, now let us see what happens. So, these are my eigenvalues for y dot equal to and these eigenvalues over here are nothing but the rate constants of this hypothetical species. So, we can write for my hypothetical species zeta dot, just as we wrote y dot equal to k y, we can write zeta dot equal to lambda 0 times zeta, whereas what is lambda 0? Lambda 0 is a matrix consisting of eigenvalues, negative of eigenvalues of, that is 0 minus k 1 2 plus k 2 1 for this particular example 0 0. So, diagonal elements are the eigen values. This is as far as the eigen values are concerned. What are the eigenvectors? We can find the eigenvectors of k, eigenvectors of k with lambda value equal to 0. What are the eigenvectors? Eigenvectors must satisfy the relationship k x, whatever is that eigenvalue, must be lambda 0 x 0. Now, for lambda 0 equal to 0, this tells k x 0 equal to 0, and when does k x 0 become 0? When does k into y become 0? K into y equal to 0 means system has reached equilibrium. So, first eigenvalue x 0 eigenvector is nothing but the equilibrium value obtained from the dynamics y dot equal to k y equal to 0. So, the solution of this is y equilibrium. So, that is my first eigenvalue, and it turns out if we take the second eigenvalue, that is lambda 1 as k 1 2 plus k 2 1, then corresponding eigenvector works out to be 1 by k 1 2 plus k 2 1 minus 1 by k 2 1 or k 1 2 plus k 2 1. Okay. So, this is x naught, this is x 1, and my y, I talked about getting that y from zeta, it turns out is nothing but x naught zeta naught plus x 1 zeta 1 for this particular case. So, what has happened? If we look at my dynamics, this is my original dynamics. The eigenvalues of this stoichiometric matrix is 0 and k 2 1 and k 1 2, and zeta 1 dot is given as we saw here 0 into zeta 0, zeta 1 dot minus k 2 1 plus k 1 2 zeta 1. So, knowing zeta naught value as a function of time, and zeta naught we know. What is zeta naught? What is zeta naught? Zeta naught is 1. So, we can write y as, and x naught is y equilibrium plus whatever is this x 1 into zeta 1 0 e raised to minus k 1 2 plus k 2 1 into t. So, we are in a position now to find y from this particular relationship. So, the original dynamics which was coupled, by decoupling it and writing it as a hypothetical species, we are now able to find the solution of the complete reaction network in a much simplified form. Okay. So, let us generalize this result now. Let us generalize this result for a general system given by y dot equal to k y. So, I have n species now. So, y vector is nothing but y 1, y 2, y n, and what is K? K is the stoichiometric reaction rate matrix as we defined earlier, but this is for a two into one system. We are now looking at more general results. Okay. So, what are those generalized results? We say that eigenvalues of this K are lambda 0, lambda 1, lambda 2, lambda n minus 1. One of that eigenvalue is 0, we know that, and eigenvectors let us say x 0, x 1, x 2, x n minus 1. Okay. So, we have hypothetical species B naught, B 1, B n minus 1, whose concentrations are zeta 0, zeta 1, zeta 2, zeta n minus 1. Now, if we know this, we can write y as x into zeta, that is the generalized form of this particular relationship. X is the vector x naught, x 1, x 2. So, if I write my x vector whose x naught vector, x 1 vector, x 2 vector and so on, then my y is given by this particular relationship. So, this is my x, this is my x. Now, let us take dy dt is nothing but x into d zeta dt, okay, and this is nothing but ky from our original dynamics. So, now let us write zeta. What is d zeta dt? D zeta dt is, so let me what is d zeta dt? D zeta dt is nothing but this x is nothing but my diagonal matrix or let's do it other way around. So, from this relationship I can also pre-multiply both sides by x inverse and I will get d zeta dt is x inverse k, and for y I am going to write x into zeta. So, the dynamics is now given by where lambda is x inverse k x. What is lambda? Remember what is our definition of eigenvector? Eigenvector is k into x naught is lambda naught into x naught, k into x 1 is lambda 1 into x 1 and so on. So, now by taking this relationship I can now get what is, so therefore, lambda is nothing but lambda 0 0 0 0 0 lambda 1 0 0 0 and so on. Only diagonal elements are non-zero, everything else is 0. So, 0 here and up to lambda n minus 1. So, that is my lambda vector. So, we now get from this. So, we know the solution of this now. Solution of this is straightforward, zeta naught is e raised to minus lambda naught zeta naught. zeta 1 dot is minus lambda 1 zeta 1 and so on. So, once we know zeta as zeta of t, we can go back and calculate y, which we did here as x into zeta. So, this gives me now y as a function of t in a completely decoupled manner. Elegant use of mathematics and chemical reactions. This analysis is known as Y and Prater analysis, done in late 60s or early 70s during that period. Okay. So, this in fact can be also used to calculate the kinetic rate constants of such system. What we need to find to get the kinetic rate constant is if you want to find k, so k is nothing but x lambda x inverse. So, from this relationship I can also write x lambda x inverse equal to k. So, to find kinetic rate constant k, I need to know x, I need to know lambda and I need to know x inverse. If I know that, I can find the kinetic rate constant. Let us look at this kind of reaction networks and its use for another class of examples. This is an example where we do not know what our reactants and what our products are, but how do we do then the lumping analysis and using this monomolecular reaction network idea. Let me give you an idea. As you are aware, if you do cracking of naphtha, you get wide variety of product, gases, liquid fuels, lubricating oils and so on. Okay. So, we get all this kind of products. Now, the problem here is chemically we do not know what is naphtha, what is its exact composition, we do not know that. We can't define naphtha as C20, H25, O blah blah blah, we can't do that. Neither can we define what these products are. Liquid fuels, petrol for example, what is petrol? We know what petrol does, but we do not know what chemically petrol is. In fact, it is a mixture, it is not a single species. So, we do not know what these reactants are, we do not know what these products are. So, let alone the reactions between them. So, we can't even know about what reactions are there, because we do not know what reactants are and what products are. So, how do we go about kinetic modeling of such reactions? Why do we need kinetic modeling? We need because we want to design reactors, and you can't always do experimentation at 1000 or million ton per annum plant and hope that you get good results. What if you do not? The entire investment will go to waste. So, we need modeling, we need kinetics to get some reasonable estimate. It may not be accurate, it is not likely to be accurate, because when we do not know what reactant and products are, how can we expect very accurate reaction network, but as accurate as possible. So, to do that, let us start with lumping all these chemicals that make naphtha as single species and say that my reaction is naphtha going to products. What those products are, I do not know. So, that is the simplest kind of lumping that you can think of. The entire crude is one chemical species. Naturally, you do not expect modeling or kinetics of this to be reasonably accurate. Then let us make another simplification. Let us say that my naphtha consists of aliphatics plus aromatics. Okay. So, two species. So, this is one species, this is two species, and then I am going to say I am going to model my naphtha reaction as something like aliphatic going to aromatic, aromatic going to aliphatic, aliphatic going to products and so on. Okay. So, some network of reaction. So, this going to something. My intuition tells me that my results are with this approximation aliphatic plus aromatic are certainly going to be better than assuming naphtha as a single species. What about three species? Let us say aliphatics, aromatics, paraffins. Just arbitrary, this is going to be better. My intuition tells me, and intuitions are always intuitions, the probability that they are right is very high, that is why we call it intuition. What if I do 4 species, 5 species, 10 species, 100 species, 10,000 species? If I do that, I certainly can expect better and better results. But the problem is, how do I define this 10,000 species and so on and so forth. So, I am back to square one. So, where to stop? Do I go 3, 4, 5? Where do I draw a line? How do I know my results are accurate? To know that, let us try to see how lumping analysis will help us arriving at this problem. So, let us go back to our monomolecular reversible reaction network and say that my reactions are A1 or AI going to AJ with kinetic rate constant Kji and Kij. I know that I can define the species concentrations as C1, C2, Cn and write dC dt in the vector form as stoichiometric matrix or reaction rate matrix, constant matrix K and C. We just now saw what is this reaction rate constant matrix. So, we need not spend time on that. Now, what am I trying to do? So, I have species A1, A2, A3, An. I am trying to see whether can I lump some of these species into an hypothetical species A1 hat. So, can I write for example, A1 hat equal to A1 plus A2. Then suppose I had 10 species to begin with, then can I write A2 hat as A3 plus A4 plus A5 plus A7 or A6 plus A7 and then A3 hat as A8, A9, A10. So, original 10 species, can I lump them to hypothetical species A1 hat, A2 hat and A3 hat, lump species, and still say that the dynamics represented for this lump species is a fairly good representation of the original dynamics. What is the connection to naphtha problem? Let us say my naphtha is a n species problem. Can I represent naphtha as a 3 hypothetical species aliphatics, aromatics and paraffins, so that we can look at the dynamics of these 3 species and still say something about cracking of naphtha. If you want to say something about original system by looking at the simplified system, we can at least consider the limiting cases. When will it be exactly same? That is, when is lumping exact? When does my 10 species are exactly represented by 3 species? Is it possible at all? Indeed, it is possible, and let us try to see how do we achieve that. So, let us go back. On one hand, we have A1, A2, AN species, which I want to write as A1 hat, A2 hat, AP hat. Okay. So, original N species lumped P species. My original dynamics is dC dt equal to Kc. I want my lump species dynamics dC hat dt equal to K hat C hat, and I am trying to see when is this lumping exact. Now, when I wrote something like this, we actually defined a matrix for this lumping. What was that matrix? If I were to write like this, then I also know that I can write C1 hat as C1 plus C2, C2 hat as C3 plus C4 plus C5 plus C6 plus C7 plus C8, C3 hat as C9 plus C10, okay, 5, 6, 7, 8, and so I want to write C hat equal to MC. M is the lumping matrix. If you look at this relationship, what do we have here? We have C1 hat, C2 hat, C3 hat, okay, for this equal to, what is this equal to? This is equal to 1 1 0 0 0 0, then 0 0 0 0 0 1 2 3 4 5, where did I 3 4 5 6 7 8. So, one more 0 0 0 0 0 9 10 0 0 0 0 1 1, and this multiplied by C1, C2, C3. So, this is my matrix M, this is my vector C, this is my vector C hat. So, can I define this lumping matrix M? When is that lumping exact? That is, original system exactly represented in this particular form. So, let us look at that and try to simplify these two dynamics and connect these two pieces. Okay. So, let us write down dC dt, which is our Kc. dC hat dt is K hat into C, and we are trying to write C hat equal to MC. So, what is dC hat dt is M dC dt, which is M into matrix K C, which we want as K hat C hat, which we want as K hat M into C, or in other words, M into K into C is K into M into C. So, what is our lumping condition then? Our lumping condition is Mk must be same as Km. This, if this condition is satisfied, then I can represent my original N species system in terms of P species. Let us take an example and things will be more clear. So, let us say that we have A1, this reaction network A2, A3 with corresponding reaction network reaction rate constants, and let us say that I want to define A1 hat as A1 plus A2 and A2 hat as A3. So, two species A1 A2 lumped into a single species and A3. So, my matrix M here is 1 1 0 0 0 1, and if we use this this lumping condition, we get the following. We get my reaction rate constant K2 hat 1, and what is our reaction now? A1 hat going to A2 hat, much simplified reaction compared to this triangular reaction network. We have just two species, one reaction. So, if I satisfy this condition, this is my lumping condition that I get, and if I satisfy this lumping condition, my results are exact. What is this lumping condition? That is what we are saying is this rate constant K31, the rate at which you get 3 from 1 is same as the rate at which you get 3 from 2. So, this particular reaction parts, that is the rates at which both A1 and A2 are going to A3 are same, then I can write this reaction network by combining A1 and A2 as an hypothetical species A1 hat and write this reaction as and this as another species and write this reaction as A1 hat going to A2 hat. Okay. Notice here that it does not matter how is A3, at what rate is A3 split into A1 or A2. There is no condition on that, it can be anything, but as long as A2 goes to A3 as well as A1 goes to A3 at the same rate, this system and this system are identical. Are they indeed? Let us just look at the results of some simulations and convince ourselves that they are indeed exactly identical. So, what we are looking at is the following. Okay. It is my same example, that is provided my what I am doing is I am writing A1 plus A2 as A1 hat and A3 as A2 hat, and let us say that my lumping is exact. So, what does it mean? It means the following. So, let us take a case that we had C1 0 or concentration of 1 is 1, second and third is 0, and we have that reaction network. What we are seeing here on the first slide is time and concentrations for 3 species A1, A2, A1, A2 and A3. Now, I choose to represent A1 and A2 as single species A1 hat, and what we see here is A1 hat as a function of time and A2 hat as a function of time. A2 hat is nothing but A3 and A1 plus A2 is 1. So, if our lumping is exact, then what do we get? We get that A1 A2 put together individual concentrations of A1 and A2 may be different, but their addition together is same. So, if you look at this 0.5, 0.5, 1, 1, 0, 1. So, as long as this condition is satisfied, we get, so here if we start with different initial condition in original species, we have different behavior compared to this. But look at the combined species A1 hat and A2 hat. These two are exactly identical. These two are exactly identical because we have satisfied the lumping condition. So, my 3 species original could be lumped into 2 species. My infinitely large number of species in naphtha, if the lumping condition is satisfied exactly, can be lumped into fewer species, 5 species, 6 species, 10 species. In fact, mobile 10 species model is most common. Now, how do I know that what I am doing is correct? For a given set of rate constant, if my lumping is not exact, and if I for example lump A1 and A3 as one lumped species A1 hat and another lumped species A2 hat, and if I start with different initial concentrations of A1 and A3, okay, A1 and A3 is still added 1, but my lumping condition is not satisfied, I get 2 different responses. Unlike here, whatever may be the initial distribution, if my lumping condition is precise, I get the same results. If the lumping condition is not satisfied, then I get two different results. So, experimentally, how do I know whether my lumping condition is correct? Experimentally, this is how it is found out. So, let us say that I have my naphtha. I lumped it as 2 lumped species. If my lumping is not correct and I trace the concentration of this lumped species by different source of naphtha, different source of naphtha will give you different distribution of your components. So, if I do that and if I get the dynamics which is different for this lumped species, then my lumping is not exact. Turns out that when you do this 10 lump species, your lumping is more or less exact. You can't be as exact as in an hypothetical example, because naphtha is a real example, but as close as we can get to the real example. So, with this we will close our discussion for this session, and in the next class we will start looking at gas solid catalytic as well as non catalytic reactions, or in short heterogeneous reactions. So, what we have done in what we can say the first part of this course is we looked at different types of complex reactions and the kinetics resulting from them, some ways of analyzing these kinetics, assumptions or approaches, for example, quasi steady state approach, quasi equilibrium approach, and then several examples such as chain reactions, polymerization reactions, kinetics of catalytic reactions, and then today lumped or monomolecular reaction network. What we are going to do in the coming sessions now is bring in transport phenomena into the picture, because we are really dealing in a majority of the cases with heterogeneous reactions. So, we will bring in transport phenomena and put it together with the kinetics and see what kind of results we get. Thank you.